Hello everyone, welcome back to Discrete Mathematics and its applications, and we continue our discussion on equivalence classes. So let's solve. Last time I asked you to solve these exercises. You were asked to give all equivalence classes of R1 and R2, and we know R1 and R2 are equivalence relations as we've seen in the previous video. So let's have a look at R1 first. So R1 is that relation, and then what would be the equivalence classes? Well, because R1 contains pairs of natural numbers, then one way is to start with a natural number, say 0, and 0 would contain all b, natural number b, such that 0 comma b is in R1. Or in other words, set of all b such that, well, 7 divides 0 minus b. Right? What are these numbers? Well, obviously 0 is there. So 0 is, because 0 minus 0 is divisible by 7. But so is 7 and minus 7. So you have plus minus 7, plus minus 14, plus minus 21, and so on. So these numbers or these integers are, well, because we are talking about natural numbers, then actually we don't need the minus, right? Yeah, natural numbers here. Now how about 1? Similarly, you will know that this has to be set of b, natural number b, such that, well, 7 divides 1 minus b, and this gives us 1, 8, and then 15 and 22, and so on. And you have similarly with 2, then you actually have 2, 9, 16, 23, and so on. And then the equivalence class of 3 is 3, 10, 17, 24, and so on. Equivalence class of 4 is 4, 11, 18, 25, and so on. Equivalence class of 5 is 5, 12, 19, 26, and so on. Equivalence class of 6 is 6, 13, 20, 27, and so on. Do we have equivalence class of 7? Yes, we do, but this is actually the same as equivalence class of 0, right? And so on, right? For example, equivalence class of 8 is equivalence class of 1, right? No, and so on, right? Now with this, how many equivalence classes are there? Well, more precisely, how many different equivalence classes are there? In total, there are 1, 2, 3, 4, 5, 6, and 7 equivalence classes. So there are 7 different equivalence classes with respect to R1. So that's R1. Now, how about R2? R2, he is here. We saw that R2 is an equivalence relation. So let's build the equivalence classes. Now, R2 consists of pair of pairs, right? Pairs of integers, pairs of positive integers, to be more precise. So what pairs are there, right? You want the pair. So the pair a comma b and c comma pairs a comma b and c comma d are in R2 if you set this if they satisfy a plus d is equal to being equal to b plus c. Now we could restate this slightly differently to make the our problem slightly easier. So let's say, so R2 is actually, so let me write this down first. Uh, yeah, this is the same as, of course, set of a comma b, c comma d. Sorry, like this. In this says that, of course, a minus b is equal to c minus d. So if the difference between the if the difference of the two pairs are the same, right? Difference obtained from the elements of the two pairs are the same. So that means, for example, if you have a comma b, so let's say a comma b is 0, uh, uh, um, um, let's right. So this is the relation. So let's say we start with a 0 comma 0. Now, what is the equivalence class of 0 comma 0? Then it would be every pair of positive integers. Oh, sorry, we are talking about positive integers, so let me just start with 1 comma 1. So pairs of positive integers such that the difference between the first and the second element is actually 1. So that means this would contain 1 comma 1 itself, right? And then, so the difference between 1 and 1 is 0, so therefore you have 2 comma 2, 3 comma 3, and so on. Yeah. Now you also have, for example, 2 comma 1 would contain 2 comma 1, 3 comma 2, and 4 comma 3, and so on. Yeah. How about um 3 3 comma 1, sorry, 1 comma 2 is another example, and this contains 1 comma 2, 2 comma 3, 3 comma 4, and so on. We have another example here, uh, say 3 comma 1, which is of course 3 comma 1, which contains 3 comma 1, 4 comma 2, and 5 comma 3, and so on. Now it seems that there are infinitely many of them, right? So can we have a general form? So let me just write this down. General form for this. Now look at this. This is the difference between this 1 comma 1 is 0, right? 1 minus 1 is 0, and the difference between 2 and 1 is 1. And this one all contains all pairs whose difference between the first and the second element is minus 1. and so on, right? So that means you consider um, every uh, positive integers, sorry, every positive integers, and then you uh, every difference of two positive integers, and you create an equivalence class of them, right? So essentially you could just write the equivalence class to be, um, say a a zero, yeah, which is set of 0 0, mm, and this is of course set of all pairs uh, a comma b of positive integers, such that a minus b is equal to 0. Yeah. Second equivalence class will be a1, uh, say a representative of it will be 1, not 0 minus, I always forgot about this. So 1 comma 1, and then this is um, it's actually represented by, say, 2 comma 1, and this is the set of pairs a comma b, c plus times c plus, such that a minus b is equal to 1. And you also have, for example, a minus 1, which is represented by 1 comma 2, and this is set of pairs of a comma b, such that a minus b is equal to minus 1. Yeah, and so on, right? So you have, so essentially for every integer k, you have an equivalence class, right? You define a k such that set of a comma b and set plus times set plus, such that a minus b is equal to b. So the number of equivalence classes that we obtain from R2 are infinite, and actually the same number as the set of integers, the cardinality set of integers. So you have these equivalence classes from R2. Now we stop here and we continue with the next video on the relationship between or some properties of the equivalence classes.